This presentation will guide you through different calculations, including pH and concentration for weak acids and bases. The first thing we want to do is calculate pH given a concentration for weak acids. We know that when we have a weak acid HA in water, it is in equilibrium with its conjugate base A- and H3O+. We also know that pH is given by the negative log of the equilibrium concentration of H3O+. We also know that Ka is the equilibrium constant for the acid, and it's defined by the ratio of products over reactants, so A- times H3O+ over HA. Now we need an ice table so that we can calculate the equilibrium concentration of H3O+. So we can write the ice table with initial, change, and equilibrium values, and we can substitute in minus X for the change in HA, plus X and plus X for A- and H3O+. And the equilibrium values are as shown. So to get Ka, we just take X squared, so A- times H3O+, divided by the initial concentration of HA minus X. So we know that the X value is the H3O+ concentration at equilibrium, and we know that pH is negative log of this X value. Now we want to practice this. We want to solve for the pH of a 0.5 molar acetic acid solution. So the first thing we want to do is write the equilibrium expression. And we write CH3COOH in water is in equilibrium with acetate ion and H3O+. And a Ka is given for this reaction as 1.8 times 10 to the minus 5. So we need an ice table. The initial concentration of acetic acid is given as 0.5 molar, and the initial concentration of acetate and H3O+ can be assumed to be about 0. The change in acetic acid is minus X, and the change in acetate and H3O+ are both plus X. So at equilibrium we have 0.5 minus X for acetic acid, X for acetate, and X for H3O+. Now we can write our Ka expression. We know that Ka is equal to X squared over 0.5 minus X, again, products over reactants, and that's equal to the given value of 1.8 times 10 to the minus 5. If we solve for X, we can use the approximation that X is small. We get that the concentration of H3O+ is 3.0 times 10 to the minus 3 molar. Now to get the pH of the solution, we just take the negative log of 3.0 times 10 to the minus 3, and we get 2.52. So the pH of the solution is 2.52. Now that we have used concentration to get pH values, we want to use pH to get concentration. So we remember that pH is defined as the negative log of the H3O+ concentration at equilibrium. So if we know the pH and we want to get an equilibrium concentration, we just take 10 to the minus pH. We also remember that Ka is defined as A- times H3O+ equilibrium divided by the equilibrium concentration of HA. So now we want to solve for the initial concentration of an acetic acid solution with pH equals 3.22. So again, we write the equilibrium reaction as shown here. We first need to use pH and then an ice table to solve this problem. So if we use pH, we take 10 to the minus pH, which is 10 to the minus 3.22, to solve for the equilibrium concentration of H3O+. So here that concentration is 6.0 times 10 to the minus 4 molar. Now we use our ice table. We can fill in the initial concentration as X because we don't know what it is, but we do know that the initial concentration of acetate and H3O+ are 0. We know that the change has to be equal to 6.0 times 10 to the minus 4 because it's equal to X, which is our equilibrium concentration. So we can fill in the table, and then we can use our Ka expression to solve for the initial concentration of acetic acid. So we say that Ka is equal to 6.0 times 10 to the minus 4 squared divided by x minus 6.0 times 10 to the minus 4, and that's equal to the given value of Ka. If we solve for x, we get 0.021 molar, and that's the concentration of our acetic acid solution. Now that we've done a bunch of calculations for the weak acids, we want to do the same for the weak bases. So we know that when we have a weak base A- in water, it's in equilibrium with its conjugate acid HA and OH-. We can use the equilibrium concentration of OH- to calculate a pOH. And if we want to convert to pH, which we usually do, we can just take 14 minus pOH. We also know that Kb is defined for a weak base as the ratio of products over reactants. So here that's the equilibrium concentration of HA times the equilibrium concentration of OH- divided by the equilibrium concentration of A-. Now we can make an ice table. This ice table is virtually identical to the one for a weak acid, except that our equation is different. So again, Kb is defined as x squared, so that's the equilibrium concentration of HA times OH-, divided by A- initial minus x. We also know that x is equal to the OH- concentration at equilibrium. So to get the pOH of the solution, we can take the negative log of x, and to get a pH, we just take 14 minus the pOH. Now we are going to practice what we just learned to solve for the pH of a 0.5 molar sodium acetate solution. We don't include sodium in the balanced equation because sodium is just a spectator. So we have acetate in water is in equilibrium with acetic acid and OH-, and the Kb is given as 5.6 times 10 to the minus 10. Now we need an ice table. The initial concentration of acetate is 0.5 molar, and the initial concentration of acetic acid and OH- are both 0. The change again is minus x for acetate, plus x, and plus x for acetic acid and OH-. Now we can use Kb to solve for the concentration of OH- at equilibrium. So we have x squared over 0.5 minus x is equal to 5.6 times 10 to the minus 10. And we get that x is equal to 1.3 times 10 to the minus 5 molar, which is the equilibrium concentration of OH-. Now we can take the pOH, which is the negative log of the OH- concentration, and we get 4.89. To solve for pH, we just take 14 minus 4.89, we get 9.11. Now we are going to use pH to solve for the initial concentration of a weak base. We know that pOH is equal to the negative log of the OH- concentration at equilibrium. Rearranging this equation, we know that if we know the pOH, we can solve for the OH- concentration at equilibrium. We also know that Kb is given by HA at equilibrium times OH- at equilibrium divided by A- at equilibrium. So now we're going to solve for the initial concentration of a sodium acetate solution with pH equals 9.42. The reaction is the same as it was in the previous problem. We need to first use pOH, then an ice table. So we know that the pOH of the system is 14 minus the pH. So 14 minus 9.42, and we get 4.58. Then we can use pOH to solve for the OH- concentration at equilibrium. So 10 to the minus 4.58 is 2.6 times 10 to the minus 5 molar. Now we can use an ice table. We know that the initial concentration is X because we don't know what it is. And we know that the initial concentration of acetic acid and OH- are both 0. The equilibrium concentration of both OH- and acetic acid are 2.6 times 10 to the minus 5. So the equilibrium concentration of acetate is X minus 2.6 times 10 to the minus 5. Now we'll use Kb to solve for X. So using Kb, which is 5.6 times 10 to the minus 10, we get that X is equal to 1.2 molar. So that's the initial concentration of acetate in this solution.